All right, y'all, welcome back to the second video covering 3.5 and 3.6. So I want to start where we left off, and I want to go back to Desmos real quick. So remember this problem involving, download speed or internet speed and download time. So if we go back to Desmos, not this one, the one we had, right? So this was our situation. Here was our data. Here's our line of best fit. Notice that trend line kind of goes through the data pretty well, right? I mean, I can zoom in a little bit to show you, but you can see that those dots are really close. So what that means is I would assume that this trend line fits this data well, and this negative association can be believed, is strong. As your internet speed increases, the time to download something is going to decrease, right? And that's just how it works. Well, if you take a look here, this program, Desmos, spits out what's called an R value. This is called a correlation coefficient. It's on the next slide in your notes. But what this means is it tells you how well your data is fitting. It talks about the direction and strength of your data. So this is a negative 0.9. The R value is going to be in between -1 and 1. So because this is negative 0.9, that's very, very close to -1. This is a strong negative correlation. We should be able to believe this trend works amongst internet speeds and download times. Okay, so this is how you find your R value. So if you have to find one, you got to do this linear regression through Desmos. So let's go back to your notes and really talk about what correlation coefficient is again. Okay, so it's on the next slide here. All right, so the correlation coefficients, this is an example. It says, what does the correlation coefficient tell you about quantities in a bivariate data set? So this is all about the correlation coefficient. So it says using technology, you can find what's called the correlation coefficient. It is this number R. It's a number between -1 and 1. That's very important, right? So your R value is between -1 and 1. Anything in between there, okay? Notice that 0 is in the middle, right? So it's -1, you got 0 in the middle, and then 1. So if I had a number line here, -1 is here, 0 is here, 1 is here, your R value will be somewhere along this continuum, right? It could be close to 1, it could be close to 0, it could be close to -1, right? There's typically 3 spots, close to 1, close to 0, or close to -1, okay? And again, it talks about the direction and strength between your two quantitative variables, which is the bivariate idea, right? Two variables. Bivariate means two variables. So if we take a look at these three graphs with their R values, their correlation coefficients listed, right? So here we have a correlation coefficient of 0.984. That is very close to 1. So because our R value is very close to 1, we're going to say it's a strong. And because it's close to +1, it's a positive correlation. And again, just as we talked about with our associations, as x is increasing, the y's are increasing. And that's what you want to see in a positive correlation. Now, if we go to the middle here, -0.2, that is not close to -1. That's actually closer to 0 if I were on this continuum, right? So what this means, and if you can tell, see how the dots are scattered, right? This shows a weak negative correlation. And again, you see the dots are just kind of scattered, like up, down, up, right? So there's no, as x is going this way, there's no pattern in your y's. Some are going up, some are going down. And then the last graph here has an R value of -0.995. That's very, very close to -1. So that means that this is going to be a strong negative correlation. And again, with a strong negative correlation, you know that as x increases, your y's are decreasing, and that's exactly what's happening over here. So there's actually a technique for calculating the correlation coefficient. We're not going to do that in this class. That's definitely something an AP Stats class might do. But we're going to talk about how they determine these correlation coefficients and your lines of best fit. And we're going to do that on the next slide, talking about what's called residuals. Okay? So and again, this is just a talking point. What a residual is it is the difference between the y value of your actual data point and the corresponding y value from the line of best fit, which is called the predicted y value. So this idea of residual is right here. It's the actual y value minus the predicted. So again, this actual comes from your data, and this predicted comes from your trend line or your line. So if you look at this picture over here, right? So we have, and I'll use this right here because they say predicted and y. We have an actual y value right there. That actual y value is the coordinates of 4, 3, right? 4, 3, okay? And we have a predicted y value at 4, and I'm going to say 4, 5. So if you take the actual y value of 3 and subtract 5, you get -2. That is the value of the residual right here, this distance right here. Right? Notice that it's a negative number because it's below the line. So this is a negative because it's below. The data point is below. All right. Now up here, and I'll do this in blue, up here we have another actual data point at, let's say, 610. And this data point, which is, I'm sorry, not that one. Sorry. The one on the line, right here. And this is the predicted one at, let's say, 6, 8. So to find the residual, if we subtract the y's, the actual minus the predicted, we get a +2 this time. That's equal to this residual. So this distance is 2, and it's positive because your data point is above the trend line. So we want the distance, the residual, to be as small as possible, because if all the dots have really, really small residuals, that means all the dots are very close to your line of best fit, and your line of best fit is probably a good one. So what do we do with these residual values? Well, we sometimes put them on what's called a residual plot. A residual plot down here shows how well a linear model fits the data set. If the residuals are randomly distributed and close to the x-axis, then the linear model is a great fit. So this is very, very, very important. So this is visually how you tell whether a line of best fit is a good model or not for your data. So if we look here, and I'm going to use my colors again. So this residual of -2, it has to line up along the x-axis at the correct value. So notice these two have an x value of 4. This x-axis matches this one, right? 0, 2, 4, 6, 8, 0, 2, 4, 6. So this is the same x value, or x-axis. But now notice your y-axis is not theirs. It's from -2 to 2. So again, 0 is in the middle. That means your residual. So this is measuring the residuals. Residual of 0 means it's on the line of best fit, the data point. And anything above means it's above. Anything below means it's negative, it's below. So if we take a look here, this residual of -2 has to be when x equals 4. So if we go to where x equals 4, that's a residual close to -2. That is this residual. So we plotted that point. Same thing here. This residual of +2 has to have an x value of 6. So when we go to 6 and we go up here to around 2, that residual is that point right there. And again, if you look at this residual plot, notice that you have a couple points above, a couple points below, and there's no recognizable pattern between those dots. This would mean the line of best fit is a good fit. All right. So again, that's a lot to take in about residuals. We just wanted to go over that with you so you heard the word before. All right. So now let's go back to here and let's talk about interpolation and extrapolation. So it says, the graphic shows regional air travel data recorded by a domestic airline company. How can you use the data to estimate the number of air miles people flew in 2003? If the trend line in air travel continues, what is the reasonable estimate for the number of air miles that people will fly in 2030? So this is your data here. So the year is your x's. Okay. Now what we're going to do here is we're going to use years from 1975. Typically, this is what you do with years, since you don't have huge numbers. So that means that 1975 is going to be our 0, and we just count from there. So 1980 is 5 above that, and then we're counting by 5s. 10, 15, 20, 25, 30, 35, and 40. And then these are our y values up here. These are the actual air miles. Now, I'm not going to make you go through this again, but I'll do it for you in Desmos, and we get a equation of y equals 47.87x plus 1345.04. Okay, so I've done that for you. So now I want to really talk about using the trend line to predict values or estimate values. And these two words down here, the first one is called interpolation, and the second one I'll use in blue is called extrapolation. So interpolation is using a model to estimate a value within the range of known values. So they're giving us two dates. The first one is 2003. Now if you look at this picture of this airplane, 2003 fits right here. 2003 is within the data range. It actually has an x value of, if I add 3 to 25, x value of 28. So if I use this trend line to find the air miles traveled in the year 2003, this is going to be an interpolation. It's going to be an estimate that I can use because the x value was within the x values used to create this line of best fit. So when I plug it in, y equals 47.87 times 28 plus 1345.04. When I use that and I type it in Desmos, right, I'm going to get 2685.4, and that's in thousands of miles. 1,000 miles. But notice that that value is right in here. So we should believe that this is a good estimate, right? In the year 2003, people probably flew that many miles. And now, let me slide this up here. Now we get into this idea of extrapolation. Again, extra. So extrapolation is when we use a model to predict about a value outside of the range. So now we're going to look at, okay, what about 2030? Well, notice that this graphic ends at 2015. That was the last known data point we used. Well, 2030 is way out here, right? The tip of the airplane. If I subtract that from 1975, or subtract 1975 from it, I get an x value of 65, way above the last x value of 40. This is a value beyond the range of values. So this is going to be an extrapolation. This prediction might not be reliable for us to use. We can still make it though, right? Y equals 47.87 times 65 plus 1345.04. And again, you just type it into Desmos, and you're going to get 3977.89, and that's 1,000 miles. But again, as you notice, right, it's way above this 3055, right? So unless we know that the trend's going to continue, which we don't know, we can't predict the future, this might not be a reliable estimate. So I'm going to put unreliable. So when you use trend lines to predict values, if the x value is within the x values used or in the data, it's an interpolation, an estimate you can believe. But if it's not, then it's an extrapolation, an estimate that you might not be able to rely on. Perfect. All right, last but not least here, correlation and causation. So we have a question here. It says a student found a positive correlation between the number of hours of sleep his classmates got before a test and their scores on the test. So as a teacher, I would say yes, you need to get sleep before a test. Those of you who stay up late at night and cram, it's not a good strategy because you're tired for the next day. Your brain can't think or work as best as it can. So keep that in mind as you're preparing for tests. Okay, so the question is, can he conclude that he will do well on the test if he goes to bed early? So essentially what they're saying is, throw everything else out the window. If I go to bed early, will I get a good test score? All right. Well, I hope you think that that's kind of goofy because there's a lot more that goes into getting a good score on a test than just going to sleep, right? You got to make sure you're attending class, make sure you pay attention and do your work, make sure you ask questions, make sure you study, right? All those things. All those other variables contribute. So the idea here is that correlation and causation are two different things, right? A causation describes a cause and effect relationship. If this happens, then this will happen. If I go to sleep or get a good sleep, then I will do well on the test. That's not necessarily going to be the case. So we have to be very, very cautious of this word causation. So to answer this question, I'm going to say not necessarily. That's a very much a statistics, like, not necessarily. I'll put a period there. Other variables. So what I kind of just talked about. Other variables such as time spent studying, right? Because if you don't study, typically you don't do on the test. I've tried to tell you guys a couple times already, but some of you start listening. So such as time spent studying could affect how well he does on the test. And there you go. And the major idea behind this is this little phrase. Correlation does not imply causation. Just because there's a trend between two things does not mean that one causes the other one to occur. Correlation does not imply causation. Man, if you take AP Stats, I think your bivariate data chapter is all done right in this 2 videos. So you're very welcome for the heads up. All right, hopefully this all made sense. If not, bring questions, and we'll see you in class.